Good day, everyone.
Hi, Toby.
What is up? Let's see. We're still coming in. I've put up the oh, okay. Yeah, I put up the not the feedback, the instructions for getting the latest changes. I'll leave them up for like a couple more minutes and then let's get going. I'm sure people are gonna trickle in for another 2-3 minutes. Today we are in for a doozy. I'm gonna talk about one of my favorite topics in Python. More iteration, yes. Right. Yeah, that's what I thought. People still trickling in one at a time. All right, I'll give it 2 more minutes and then I'll get going. For those wondering why I look like a defeathered chicken, that's because I just cut my own hair. Fun times. All right. Let's see. I'll be back in a sec. Okay, welcome everybody to another lecture. Today we're going to talk about yet again one of my favorite topics in Python, which is iteration. We are going to have a lot of fun. For those that are coming in a little bit later, I'll just copy the link in chat again for the instructions on how to get the notebooks. Zip. Instructions on how to get the latest lecture. All right, and let's jump right in. Zip, zip, zip. Where are my? There we go. Okay. And I've just performed these myself, so they work. In my case, I just use git status. Everything was up to date. You can still do git add and git commit. It'll just tell you, well, there's nothing to commit. And then I did git fetch, got the latest updates, switched to the correct branch, and here we are. And I'm gonna exit this terminal because we don't need the terminal today. In today's lecture, we have some fun data set. Oh, Jesus Christ. About film permits in New York City, so I'm excited to talk about that. But first, let's talk about higher order functions. That's going to take a second. It'll realize. Yeah, exactly. It'll realize. Oh, Lordy. Okay. It'll realize the correct Python extension, and then it will load, hopefully. And yep. computer is melting right now, so that means typically that something else is taking up too much space. Let's see. Yeah. Let's see. Let's close this and open this again. Sorry, folks. Oh, yeah. There we go. Okay. Cool. All right. Let's get going. Today, we are going to talk about higher order functions, especially map, filter, and reduce. We're going to learn just a teeny bit about generators. We're going to learn about anonymous Lambda functions and some examples of how to use those. And then we're going to, in the end, like I try to do with kind of every lecture that I've given so far, kind of combine all of those things we've learned into one example where we try to maybe do a little bit of data analysis. And then in the very end, there's like an extra section of some stuff that I find very exciting. You don't have to read through that stuff, but that's like extra credit, I guess. Like if you're extra curious, you can read the last bits on your own. So just a quick recap on functions. So far, we have learned to write functions as a way to generalize some operations so we don't have to write the same code repeatedly. And for example, if we wrote a function sum x comma y, where x and y are the arguments and sum is the function name, that would perform probably addition over any input numbers, right? We wouldn't write a function that just knows how to calculate 1 plus 1. We would write a function that can add any two numbers to each other. And functions can take in objects as arguments. And so far that's always been, for example, lists or integers or strings. So like this neat little quaint function here, which is called greeting, which takes in a list of names and then does some string manipulation and then prints out the greeting, right? And today we're going to talk about higher order functions. So everything that a function can take in as an argument has to be an object. In Python, most things are objects. There are very few things that aren't. And functions themselves are also objects. So functions themselves can be passed as an argument to a function. And that's exactly what higher order functions are. Higher order functions are functions that expect another function as one of their arguments. And you already actually know some higher order functions which take a function as an argument to decide how to order values in a sequence. And those are max and sorted, and also min, and there's a couple of other ones that you know as well that you can use as higher order functions. And so here I've written up 2 examples of why this might be useful to pass a function to max or sort it other than their default mechanism for deciding how to order numbers or any kind of variable, really, right? So here, for example, we have defined a function that takes some integer and then computes the digit sum. So the sum of the digits. So the digit sum of 158 would be 1 plus 5 plus 8 would be 14. And there are contexts where this kind of could be useful. And let's see how that works. Zip. So here we have numbers 11, 9, 23,000, and 152. And basically we can use the max function to figure out the number with the maximal digit sum. And in this case, that number is 9. which is kind of unintuitive, right? Because there's all these other numbers that are larger. So it's hard to, like, at a glance know which one of these has the largest digit sum. And then we can also sort by this digit sum. And similarly, I have another example here where we order, let's assume we have a bunch of primers and we want to know the fraction of GC content that they have. And again, this is relatively straightforward stuff. We take in some string, we lower the string, we lowercase the string, and then we count the lowercase g's and c's, and then we divide that by the length of the string, and that is the fraction of GC in that string. And so that way we can relatively quickly with max or with sorted figure out things about our list of primers here. And again, right here in this example, we just have 3 primers, but you have to think about, well, what if you're designing some massive experiment and you're generating thousands of primers or hundreds of thousands of primers, right? Then this kind of thing becomes useful. And so you can already see that, like, we could have, of course, written this all with a for loop, but the fact that the max function just takes in this ordering function, and so does the sorted function, makes it so we can do relatively really complex behavior with really just very little code, which is we define this function, and when we pass it on to these higher order functions. And so in general, whenever we use these higher order functions, we use them because they can be used to build kind of very powerful abstractions that generalize over many different processes. So one typical example is like any kind of formatting. Very often, if you have some kind of function that gives some kind of output, and you want to apply some formatting to that output, very often that will be open to use applying your own function to do the formatting of, for example, time or plotting style or printing style. There are libraries that let you authenticate in web applications, and there often you can also supply your own functions to handle that authentication, to connect to a database, et cetera, et cetera. So it's anytime you have some kind of general thing you want to do and you expect your user to, after the fact, want to alter some kind of behavior, and you don't know that you can anticipate everything that the user will want to do, you just say, okay, I'll supply like a default function for this part of my process, but then you can supply your own function as one of the arguments to change part of the behavior of this function. And this is all sounds very abstract, but we're going to go into a concrete example right away. This helps achieve modularity, meaning we break up functionality into truly reusable pieces. That makes our code typically easier to read, easier to test, easier to debug. And composability, this is like, again, kind of a bit of a question of taste, like, you know, season to your own taste. You'll write a number of functions with varying inputs and outputs, and some of these functions will be, you know, unavoidably very specialized to whatever particular application you're writing, but others will be useful in a wide variety of programs. So for example, let's say you're doing something with image manipulation and you're writing a function that takes a directory path and returns all the image files in that directory. That might be useful for many other of your projects as well. And last lecture, Mark showed us how to write your own module so that you can easily make that functionality available in future programs you're writing. And then if you took this function, you could even generalize it further and say, well, you just write a function that takes a directory and a function and then applies that function to all files in that directory, right? So you can see how you can always go more and more general, and how general you want to go is really up to you as a programmer. It can often save you a bunch of headaches when you generalize a little bit further after you've kind of copied and pasted the same code a bunch of times. But it also can create a bunch of headaches when, before even writing any of the other non-generalized code, you just generalize everything. So there's a balance there, and that'll come with experience, I think, to the feeling for how to strike that balance. So here we have an example. We have three functions here, and what they do is they print a name with some kind of string formatting here. So it's hello and then name.upper, or hello and name.lower, and hello and name.title. And you can already tell from this example, right, all these three functions are doing is they all take a name, and then they all print something, and they all kind of do the same formatting. The only thing that changes between these functions is how this name attribute, this name argument is formatted, if that's going to be changed to uppercase, lowercase, or to title case, all right? And so if we were to write that in a more general fashion, we would write a print greeting method that just takes in a name and a method, and then applies the method to the name and prints the name. And then we have three other functions that we write that just do the string transformation, right? In this case, name.upper, name.lower, and name.title, right? And so we can see, so we can see this prints, well, hello mythos, with mythos capitalized, lowercase, and title case. And in this formulation, we get the exact same results, except now if we wanted to change something about this part, we would only have to change this print greeting method. So if we wanted to write like nice to meet you, now I only had to change this one method, this one function, instead of changing all three of these functions. So again, sometimes this can be very useful when you have to do something over and over again. And for me, my kind of general rule is, if I find myself copying and pasting something more than once, then I'll probably think about kind of factoring out that part of the code and see if I can generalize it so that it can break it up into different functions. Now we're going to learn about a new way of writing functions. You've seen here in this example that we have these like very bare bones functions like capitalized, lowercase, and title case, where all they really do is they do string formatting. And if we do this a lot, this might be nice to have a function for that's called capitalize or lowercase or title case. But generally, for these kind of formatting examples, oftentimes it's not really necessary to like write a whole function. And usually, you know, if this was a fully fledged program, you would also want to write like a doc string, right? And so you would want to write documentation for it too. And so that can quickly turn into a lot of code you have to write to achieve very little. That's typically not where we want to be. And so for simple stuff like that, we use what's called Lambda functions. And they, I think some people find them very scary, but really all they are is they are a useful shortcut for writing small functions that we create at runtime, like the string formatting examples I just went over. They are a single expression, and the value of that single expression is returned. And again, this is only to be used for like very simple stuff. If you have a harder time, if you spend like 5 minutes or 10 minutes debugging a Lambda function, that you could have just written a regular function and you would have figured out how to write that. And just write the regular function. Like there's no point in squeezing everything into Lambda functions. And the syntax for Lambda functions is Lambda, and then here come your arguments, and then you can even do something like this: star args and star keyword args, star keyword args. I don't know how in depth we've talked about these this kind of notation, but just as a reminder, this basically would take, you could supply any number of arguments, and the first two in this example would be x and y, and every other regular argument would then go into args, and then any keyword arguments would go into kubargs here. So this is just typically a pattern used for making sure that the user can supply kind of any number of arguments, and oftentimes you'll just pass the remaining arguments onto the next function, and the next function will then just pick out the arguments it needs, and so on and so forth. And then here we write an expression, and then what we get if we use this function is we get the return value of that expression. A couple of things we cannot do in Lambda functions is we cannot do assignment, for example. So you can't keep track of variables in here other than these variables that you define here in the argument section. So again, if you have to do something more complex, just write a regular function. But here, to go back to our example we just went over, right? We can just we keep our print greeting method the same, and then we can just as the method argument, right? This is the method argument. We can just say lambda name, name.upper, lambda name, name.lower, lambda name, name.title, right? Instead of having to write, you know, 3 more functions like we did here, which take up space. We have to probably maintain these. Whereas if we write a lambda function, typically what we say, what we kind of express by writing these lambda functions is, this is a throwaway function. This is nothing special. We didn't think this was important enough to make kind of, you know, future-proof and maintainable, because you can also not import lambda functions. One of the things that's, that I mentioned earlier is that these are anonymous functions, and that means they don't have a name. Their name is always lambda, so you cannot import a lambda function from like a Python file. So if you want your function to be importable, again, write a regular function. All right. And so one of the reasons why I wanted to talk about lambda functions is because, I mean, in this example, it's really quite simple, but these are very useful for when we chain together a bunch of these higher order functions that take in functions as arguments. We can, on the fly, kind of in our code really quickly define these lambda functions without having to write like def and then function and then arguments and whatnot. This is kind of a very compact way of experimenting with functions. And here we have some more examples of lambda functions being used. I've copied this down here. So here, for example, we have a list of genes and transcript counts. So it's gene 1, we have 2. For gene 2, we have 4, and so on. And if we sorted that, it would sort, I think, by default by the first item in the tuple. And then if we sort and give sort, again, lambda function as the key argument, and we say the key for sorting should be the first item. So the first item in each tuple is this. This is the first, this is the 0th item. So we would sort by transcript counts. then we see it sorts properly according to transcript counts for us. And here's another example. You can also do this when you have, for example, a list of dictionaries, which is kind of similar to what we'll look at in the data analysis example later on. So here we have a bunch of Hobbinsons, and we want to either sort them by first name or last name, and because we can just quickly write this Lambda function here on the fly, this takes, again, relatively little code to sort these hobbits by their first or last names. All right, with that out of the way, we have another example here about using this to group kind of complex objects. So itertools, again, kind of an all-star, has a function that's called group by, and we can use that to take a larger iterable and group the items in that iterable by some kind of quality that they have. And so here we have a list of cities, and each city is in a different state, or some are in the same state. And so we basically want to group these cities by state. And so here again, we could write a get state function here, which all it does is it's one line, and all it does is it returns the first item. That's not really super useful to us. We probably won't need this function very much. It works this way. Oops, what was it? It works this way. So what we're doing is we're making this groups iterator by using itertools.groupby, and then giving groupby the city list, and then giving it our get state function. But we can, and then here we just iterate over the groups and the iterables for each group, and then we print the groups. But what we can do instead as well is we can just use a Lambda function for this, and zip, comment out all of that, and this works just as well. And we'll actually get back to this group by function a bit later. One of the kind of tricky bits with this is that the keys already have to be sorted. So the list in this case already had to be sorted by state. If this was, if these were not ordered this way, we would have gotten like multiple groups for the same state. But we'll talk more about that later. All right, so let's get talking into the kind of meat of this, which is why we want to learn about Lambda functions and all this other stuff, is we want to use these really powerful built-in higher order functions that are used very often with iterables in Python. And one of the all-stars is called map. This lets us map or apply a function, any function, to each element of an iterable. And this is very, very common operation to do on an iterable's output. For example, let's say we have a list of strings. You might want to strip off leading and trailing white spaces, or log transform each value in a list of numbers. And you can already see this is somewhat similar to just writing a for loop. There are some differences, and you can definitely still keep on writing your for loops, but we'll see a little bit later as to why it might be preferable to use map for some of these jobs. And it generalizes the process of transforming a whole collection, both the data collection as well as the transformation functions are provided as an argument. So map always takes in first a function, and then you can give it any number of different iterables. And then it'll, map will not evaluate immediately. So map is lazy again. So when you define this, when you call this function, all it does is it says, well, okay, this is this function, and this function has to be applied to these iterables. And then when we ask for items from map, what we get is the function applied to the first item or the 0th item in each of those iterables, then the function applied to the first item in each of those iterables, and so on and so on. Map returns what we call a generator. It's a type of lazy object, which instead of returning values, it yields values one at a time as we ask for them. Generators are another form of iterables. So we can give map, for example, another map object as an input, and we'll see later how that can be very powerful to chain multiple maps successively. We can ask the generator to yield the next item by using the next function. We don't very often use that in actual code. Calling the next function, most of the time, we will just use other higher order functions that do this for us automatically. They keep asking for items from the generator as they need them. Generators have no length, so they're not lists. They don't know how many items they have. Generators can be infinite length, can be finite length. The generator has no way of knowing what its length is. We cannot, for that reason, we cannot index a generator. So we can't say we want the first and the second item. It won't know what that means. But the itertools library gives us a function called islice, which if you go into the kind of extra credit section, there's a little bit about islice, which produces a generator with the slice that we're asking for. Remember slicing, slicing was this kind of, if you have some list, if you have some list and then you say, start, stop, and step, this is what we call slicing a list, right? And so islice lets you do that for any iterable, and it returns a generator-like object. Another thing that can be kind of annoying with generators is you can only iterate over a generator once. It's not like a range, which is also lazy, but can both be indexed and iterated over repeatedly. And a generator gives one item at a time. It just keeps track of where it is right now, what state it has right now, and then computes the next state based on that. It can't go back in time. You can't go over it multiple times. So oftentimes when we want to have the items in a generator and want to be able to iterate over them repeatedly, what we do is we consume that generator. And that means we're asking the generator for items until it can yield no more items. And we will use the list function for that, for example, and make a list out of all the items in that generator. So this is just a little bit of theory and how just so you don't get surprised when these map and some of the other functions we're going to talk about later, when they don't behave exactly the same way you're thinking about them. That's why I wanted to talk a little bit about generators real quick. And so here we have some examples. I think I've copied them below already. I have not. Let's see. So here we have, let's go and here. So here we are importing square root from math, and we have a list of numbers, and all we want to do is we want to map square root to this list. And let's comment this out for now. So print the type of the result and the result itself. And what we see is it's a class map. And all it tells us is it's a map object at this location in, oh, somebody asked about islice. Would you need to know where the slice you want is beforehand? Then correct. Yes. you would want to be able to specify that before. Again, there's more on islice in the kind of last section. We're not going to be using it much here. Anyways, back to this example, we just see the space and spot in memory where this map object is. If we want to know, if we want to consume all the items in the map object and make it actually, you know, get off its lazy bum and actually do the computation, we have to consume it, say, using, for example, a list. And so this prints out the square roots of these numbers, and this is now perfectly accessible. Now, one thing you can look at now is you can print result now, zip. And it's still a map object, but now if we call the next function on the result object, next, it'll tell us stop iteration. That means the generator is empty. It's not able to produce any more items. And that's because in here, we use the list function to consume this generator. So that means we empty the generator, there's nothing left in results. Right, so if we run this section again, so we make this result map object again. Now when we call next on this, it gives us the first value in that list. And now if we call next again, it gives us the second value, and so on, and so on. So you again see how this generator paradigm works. And then it tells us, oh, stop iteration. So basically, there is no more item in this generator. Again, we don't usually access items in the generator using next. This is what these functions like list do under the hood, is they keep asking for items until they get a stop iteration, and then they stop. All right, and here is the next example is we're going to look at something we actually did in a previous lecture where we had two vectors and we wanted to compute the dot product of them. And in the previous lecture, what we did is we basically iterated over the length of, over the range of the length of these vectors, and then manually basically picked out the elements from both of those vectors, multiplied them to each other, and then summed them to some variable called dot. Here what we can do is instead is we map a quick Lambda function. Is it better to use a map generator to deal with a large data set or converting the data to NumPy array? Yeah. The map generator has, the map generator depends on, so somebody asked in chat just for the recording about is it better to deal with large data set with a generator or with map or with NumPy. That depends on how large your data is. As long as your data comfortably fits into memory, you want to use NumPy for mostly because it's much faster. It's about 100x faster than Python for most common operations. Whereas if you have, with this kind of map, you can technically run this over an infinitely large data set, because all this does is, and then if you filter this map, all this does is it does one computation at a time and returns the value. And in our case, we're using sum here, right, to compute the dot product. So sum will take basically two values, one value from here at a time, and add it to this sum, add it to the sum. And so this is very, very, very efficient. So you could use this to loop over terabytes of data, and your data usage would never even, you would never even notice the data usage. However, again, if you want to do very heavy duty numerical computation, you probably want to use a NumPy or pandas. And I'm kind of hinting at this in the end notes from this lecture. That's what we're going to talk about next lecture. That was a quick detour. Let's get back to this example where what we want to do is we have two vectors. We want to compute the dot product, which is basically multiplying these elements, doing element-wise multiplication. So 1 times 5, 2 times 6, 3 times 7, 4 times 8, and then adding those all together. And so what we do is we map this lambda function, which multiplies two elements, to these vectors 1 and 2. And then we sum the result. We sum whatever comes out of this map generator. And that gives us the dot product. In Python, quick note, in Python 3.8, we could use a math.prod instead of this lambda function, but we're in Python 3.6, so we don't have that quite yet. And here what you see is, I'm not going to rerun this. I did some benchmarking on this with vectors with which I populate randomly, and very large vectors here. I think it's like, yeah, 10 million in length. The map, sum and map way of doing this is actually like about 20% faster. And I reran this a couple of times and it's pretty consistent, and also consistent at different sizes. And so I wouldn't say that that's a reason why you should definitely use generators, but one of the reasons is it's very memory efficient. It will basically do one computation at a time as needed and never keep more in memory than needed. But yeah, so this is just basically another way of doing that, what we did last time. And let me just copy and paste the other way of doing this, which was this way, which I think a lot of people will, when they start out writing programs, they will find this way a little bit more intuitive, where what they say is, well, we say dot equals to 0, and then we iterate over the length of these vectors, and then we ask each of these vectors one by one for an element. And then what we do is we add the product of these to this dot variable, right? I think actually the reason why this map way is faster than the for loop way is because we're doing this indexing. And while this indexing is fast, it takes some amount of time. And that's why the map way is faster, I'm pretty sure. There is yet another way we could write this, where we could say, instead of, we could call these again L1, L2, and there is a neat function that is called zip, which is also one of my favorite things to say. And what zip does is it returns an object whose next method, so when we iterate, it returns another iterator that gives us basically one item from the top of each of those, of each of the iterables that we gave it. So this would give us at first 1 and 5, and then it would give us 2 and 6, and then it would give us 3 and 7, and then it would give us 4 and 8, right? And then we could, again, write this like L1 times L2, and that works just as well. And this way would, I think, actually, and I think this way would actually be probably just as fast as the map way that we did here. But again, this is just another way to rewrite what we did there previously. We can also use map in conjunction with functions any and all, which are Boolean functions. They check a Boolean condition on a whole, basically, iterable. So they see if either any of the items in that iterable are true, or if all of them are true. This comes up actually quite often when we need to quickly kind of sanity check our data. So in the following example here, we have only 3 items in a list. But again, most of the time we'll have hundreds of thousands. So being able to check quickly if any or all of them fulfill some kind of condition is faster than just printing the list and looking at the whole list. Additionally, actually computationally, any and all are faster than just one by one checking the items in that list and checking the whole list if there are any trues or falses in there. Any and all will give an answer as soon as they can. That means when any encounters the first true, it'll return true. It won't keep asking for more items from the iterable. And when all encounters the first false, it will return false because, well, not all items in that list or iterable are true. So it can already give you an answer. So in our case, this means that we won't, that any won't consume all of our map generator object only as much as it needs to provide an answer. So let's assume we have written a program that made some DNA primers for a massive PCR experiment we're designing. This is actually something I've done myself when I was working on a previous project. So this is, I would say, quite a real scenario that can come up. And we want to quickly check if the GC percentage of any or all of them is below 0.5. And so here, excuse me. So here we have a function that's called GC fraction, takes in some DNA string, and then it'll return the GC percentage of that string. Again, relatively simple. We just lowercase the DNA string, we count the G's and C's, and then we divide that by the length of the DNA and we return that. And so what we can do is, here we have our primers, we can use any and map this Lambda function to our primers, which basically checks if the GC fraction of each primer is smaller than 0.5. And so you can see any takes in this map generator directly. We don't have to do anything in between. It's relatively quick to write. So what I've done here is split it up. Here we have our primers, and then here we have, basically, if we split that up into lines real quick, we have our any function. That's kind of the outer function, is a bit like an onion. And we have our map function that basically maps this Lambda function that returns that asks if the GC fraction of an item is smaller than 0.5, which we've mapped to the primers here. And so if we ask this, and I mean, just looking at this list, you probably wouldn't be able to immediately tell which of them has a lower GC fraction. And then maybe that's good. So just knowing if any of them are true is good to know. But if we want all of these to be that, we want to check if all of them are fulfilling that condition. And in this case, it turns that's not the case. So did folks kind of grok what's happening here, that we're using this map function, which is basically similar to a for loop, but it's lazy, and applying this function that we wrote here to this primers, and then we use any to consume this map object. Are there any questions about map so far? Okay, nothing seems to pop up, so I'll move ahead. Another function, does any stop at the first encounter? Yes, that's correct. Any will not consume the whole. But you can run the any and all sections over and over and not hit stop iteration. Why is that? So the first question was, does any stop at the first encounter of GC? percentage smaller than 0.5, and that is correct. And the second question was, previously was stated that map doesn't save previous states, but you can run the any and all sections over and over and not hit a stop iteration error. Why is that? Well, there are two possible reasons for the second question. One is we are making a new map object every time I'm running this. So of course, every time I'm running this, it's making a new map object. And so when it's making a new map object, it's a new generator that starts from scratch. So that's why you can do that repeatedly. Another reason would be, and this is why I think this is a great question, is we can actually save this map function to an object. Let's call this object, our map. And we can ask if any is true of map, of our map. There we go. And this returns a true. But now we can run this again, and it returns true again. And the reason for that is there are multiple items in here that this expression returns true for. And any actually only keeps asking for values until it hits a true, right? And so because it's hit a true, it doesn't consume the entire generator. So if I ask one more time, it'll ask false. And if I ask one more time now, it'll still say false. Huh, this is quite interesting. It keeps one item in there. It only looks at the top item. That's quite interesting. It doesn't actually raise a stop iteration error there. Huh, interesting. Learned something new. So it looks like it doesn't pop the last item here, which is fascinating. I did not know that. But you can see this behavior of any taking only one item at a time, only inspecting the top of the generator. All right, let's move forward. A next all-star is filter. And so basically a lot of my code that has to do with this generator stuff is mostly just maps and filters, really. Filter is another common higher order function that we use on elements of an array, and it selects a subset of elements that meets some condition. So the syntax is filter predicates, comma, the iterable. So the predicate is a function that tells us, that returns either true or false. And the iterable is our iterable, and so filter will only keep items for which this predicate is true. So for example, let's copy this stuff. Here we have a function that we call isEven, and let's say we make a list here of this filter object, which this filter object is we apply this isEven function to our range of 10. And what this will do is it'll give us back only the even numbers, right? I think people understand. I hope people understand how this isEven function works. What we're doing here is we are doing a mod division by 2, and then if that has no remainder, meaning if the remainder is 0, then that means that that x was even. So again, this is, you'll see a lot of these kind of onions. If these intimidate you, don't worry, you can just separate them over multiple lines. So now, and Jupyter is unfortunately not very good about kind of properly indenting that stuff. Oh, good. Ben looked up the help for any and all, which says that if the iterable is empty, any returns false and all returns true. So it did pop the last item, but it has a default value instead of an error. Yeah, that makes sense. That makes sense. That's good to know. Getting back to this item, this example, basically we have our print statement, that's the outer part of the onion. Then we have our list statement, that's slightly more inner. And the most inner part is we have our filter function, which applies this isEven function to this range of 10. So we are looking at the values from 0 to 9. and only giving back the ones that are even. And list we have to use to actually make this filter function do anything. It's a lazy function. It gives us a generator. And where this becomes nice is where we can combine filters and maps and that kind of stuff. One more function that we have to look at here is called reduce. This is not one that I use very frequently myself. This is something that's kind of more that people got really hyped about a couple of years back for like kind of doing very, very big data analysis with Spark and Hadoop, that kind of stuff. So anybody who's heard of the like filter map reduce or the map reduce kind of computations, that's the reduce that this is referring to, which is another higher order operation which cumulatively performs an operation on all the iterables items. Which what it does is it aggregates an iterable to a single object. And this used to be part of the built-ins, but in Python 3, I think got moved to functools. So we have to import functools, and then the syntax is functools.reduce the function, then the iterable, and we can also give it some initial value that it starts from. Func must be a function that takes two elements and returns a single value. So that way it can basically iteratively kind of crunch an entire iterable into one value, right? By always taking two and crunching them together and then taking the next one and combining it and so on and so on. And it takes the first two elements of A and B returned by iter and then calculates function A and B, and then it requests the third and so on and so on. So here we have an example. We import reduce from functools. Then we have a sum function here that we've written, our own sum function, sum underscore. And what it does is it prints the arguments A and B, and then it returns A plus B. And so here we have our, we have X, which is just a list of 1 to 4, and then we have a result here, and then what we do is we reduce X using the sum underscore function. And what this does for us is it basically this first takes the first two items in this value in here, right, which is 1 and 2, sums them, which is 3. So the next items that we get is, well, 1 and 2, which is 3. And then the next item from X, which is 3. So 3 plus 3 is calculated, and then we get 6 as the next item that reduce receives. And then the next item from X is pulled, so we get 6 plus 4, and that is 10. And we've written that out here to make it a little bit more easy to look at, right? It's basically 1 and 2 get summed first, and then 3 and 3 get summed, and then 6 and 4 get summed, and then we arrive at the end. This is just demonstrating that reduce can also optionally take an initial value. So the same example that we just had, instead of this sum underscore function we wrote, we can also just give it a lambda function that says A comma B, and it returns A plus B. And if we give it a starting value of 100, then, well, the output would be 110. Again, functools and itertools, great modules, have some great stuff for using generic higher order functions. Got a typo in there. And now is the part of the lecture where we're going to try and kind of put it all together into a couple bigger examples. So combine, especially map and filter, and also some of the other generator functions allow us to do really relatively complex tasks in quite a few lines of code. We can use those to build or transform lists with for loops. We can build and transform lists with for loops and if statements. And analogous to that, we can also just use map and filter, as we just discussed, right? Map is basically a for loop, but in form of a generator, and then filter is if statements. And nested if statements, that's the important bit. So I've given you an example here. We want to give the sum of the square of all numbers that are below 1,000 and are divisible by both 5 and 3. And this is kind of a generic mathy example, but you can think about this. You know, oftentimes we have like a bunch of genes, and maybe they're in a bunch of different gene families, and we want to subset, you know, oh, are they in this gene family and maybe also in this gene family? Or, you know, is it in this gene family and also is the gene count this high or something like that? So this kind of chained filtering is a thing we do quite often, actually. And so the way to do that with a for loop would be to, well, initialize the sum at 0, and then for each number in the range of 1 to 1001, if the number is divisible by 5, if the number is divisible by 3, add the square of the number to sum, right? And you can see how, well, here this is pretty simple because we're only doing kind of one thing in this nested for loop. But as you're doing more stuff in these for loops, it can get quite hard to read. And now many of you will say this next example, which is how I would probably write this, is maybe not that much easier for you to read. Again, write what you're comfortable with. Just know that when this becomes unmanageable for you, this may be a way to relatively easily break this up into multiple loops. Because one of the problems with these nested for loops is, since we've nested these if statements, that increases our efficiency, right? Because the second if statement is never evaluated if the first one isn't true. So we save some computation that way. And so we can't that easily break this up into multiple for loops without losing efficiency. So let's make a new field here. We can write the same thing using these higher order functions, where the stuff that's basically more up or higher up in the for statement in the for loop is going to be the most inner part of our onion. So we're basically reversing the for loop. So we're going to filter. Let me just make that clearer here. We're going to filter the range of 1 to 1001 by items that are divisible by 5, and then we're going to filter those by items that are divisible by 3, and then those that come out of that we're going to square using a map, and then we're going to sum the whole thing using the sum function. And one thing you can do is you can break this apart at any of these steps. So you can say, okay, well, this is now our first filtration step, right? First filter. And you can say, well, maybe this is our second filter. Second filter is filter of this lambda function and then the first filter. And then we can just put the second filter in here. Zip, and then we have one too many parentheses. And so all of a sudden we've kind of cleaned this up, this relatively nested code up into less nesting levels and still retain the same efficiency. And this gives us the same example. Let's go and analyze some data. I have downloaded some film permits data from NYC Open Data, and we will try in the following and answer first quickly what type of events are in this data set, and then we'll ask what is the average and the median length of a shooting permit by borough. It's a relatively complicated question, right? We have kind of a bunch of different things that are going on there, and what is the standard deviation? Before I get into that though, are there any more questions? Do people want me to explain this example here again as to kind of how everything works? I know from my own experience, this is not maybe the most intuitive way to think when you start writing this way, but it has a couple of advantages. Sometimes it can be more efficient, it can be more maintainable or more easier to overview in the long run. Is it actually helpful to denest the filter statements? No, that makes no difference. The only difference you're doing here is you're doing one assignment that doesn't cost you any efficiency. One reason why I actually like, especially when I'm kind of trying out stuff, writing my code this way is because I don't actually have to think of any variable names. I actually like nesting the stuff like this, especially when I'm trying out stuff, when I'm trying out things and exploring my data. Because one of the hardest things actually is to come up with variable names that are reasonably long, reasonably short and understandable. And so this is one of the ways I kind of circumvent that. Another reason is that you can relatively quickly change out the parts in these filter statements this way without having to kind of, mess with the nesting loops of your for loop. Question, back to reduce. By itself, reduce cannot make code more efficient, right? So what the efficiency gain you gain with reduce, and the reason why it's so, maybe not this like base reduce, but like the reduce that's available through Spark and I think Hadoop. The reason why that got so popular is you can have reduce always takes the same amount of memory for each calculation, right? All it does is it keeps in memory at most 3 items at a time, right? The 2 items that you give it and then the item that it returns. So the memory consumption of reduce is constant. It always takes the same amount of memory, whether you're using it on 15 items or 15 million items, right? And so, but again, if you had such a large amount of data, you would probably use software that's more specifically tailored to dealing with these incredibly large data sets, like, for example, Spark or Hadoop. This will not come up for most people. And there are other ways of dealing with data that size, namely using a cluster, which is what most of us do when we can't work with data on the laptop. But yeah, reduce doesn't make your code faster or anything. It just has constant memory use. And again, this is the appeal of using these filter functions and map and lambda and whatnot, is they have and map and filter and reduce is they have, unless you have some kind of memory leak in your functions, you will have constant memory use. I'm pointing at the end of these notebooks to some talks that I really like. And one of them is on the topic of generators. And there's a guy called James Powell who does some really, really crazy stuff with just base Python. But he's more of a wizard than I am. I'm just a henchman here. All right. So that seems to be it for questions for now. So let's dive into the data. Again, I downloaded film permits data from NYC Open Data. NYC Open Data is a cool platform where you can download all kinds of different data about New York City, like where were rats reported to be seen the last time, or where were the last noise complaints, or where were the most bike accidents, stuff like that. So when you're trying to do some projects of your own to get more familiar with this stuff, I really recommend looking at NYC Open Data and seeing if you can download some data and play with it. So first, we will read in the data using the CSV module. The CSV module lets us read CSV files, CSV standing for comma-separated values. And so here what we're doing is we're opening our file in this with statement, and then we're listing the film data from the CSV dicta reader, and let's take a look at what the first item in that list looks like. So this takes a hot second to compute. And so basically each of the rows in our CSV file is now a item in this list film data. And each of these items is an ordered dictionary, which has many different fields. So event ID, event type, start date, time. So this one, for example, is a shooting permit. And there's all kinds of other stuff, event agency. And one of the other fields we're interested in here is borough, right? So this one is a shooting permit that's happening in Manhattan. So first, let's see what type of events are even in the data set, right? And this is actually a relatively quick thing to do here. Given our film data, what we're going to do is we're going to map to it a Lambda function, which for each event in this film data list, it's going to access the event type field from this ordered dictionary. And then we're going to use set. Why are we using set? The reason we're using set is because it gives us only unique items, right? So basically, what set is going to do is going to take the stream of event types from our film data, and that it's going to only keep items that are unique. And so here we see those can be decast, prep, shoot, wrap permits. We can have rigging permits, whatever that is, shooting permits, and theater load in and load outs. Learn something new. And so this was a relatively quick and simple question to answer. But now let's go to the more involved question. And that is, what is the average / median length of a shooting permit by borough, and what's the standard deviation? So this is the kind of question we would think about for our biological data analysis often, right? We'll have some kind of grouping, and we want to compute some statistics over our data, and that requires us to kind of think about how we want to structure our code so we can actually answer this question. So here the thinking process for me was, well, first we want to filter the data to only include shooting permits. Then we want to group the data by borough. Then we want to parse the start and the end times of these permits and calculate the time difference in days, because if you look at this is just a string. This is not like some integers or something, it's just a string. So we have to somehow convert that into numbers. Exactly, so we have to parse start and end time of these permits, calculate time difference in days. And then once we're done doing that, we calculate the aggregate statistics for each borough. So this is like quite a lot of stuff. Even for me, this was something where I don't just like off the top of my head write the whole thing in one go. So I typically break this into multiple parts, and especially I didn't know how to do this this time parsing specifically, and how to do this time difference calculation. So I'll walk you through kind of my process of how I would go about kind of testing out my ideas and then writing it all up to actually answer this question for the whole data set. And so in this case, when I know there's a part of the algorithm that I will have to do a bunch of testing on, what I use is I pick one of the observations in my data set to test on. I usually name it dummy because I'll make a lot of mistakes, and that's okay. So let's pick the first item in our data set here, right? We'll call it dummy. We've seen this item before, but this just makes it a little bit easier for us to kind of cover all of the rest of the algorithm. The other parts, the aggregating the statistics, we can just import the mean, median, and standard deviation from statistics, so we don't really have to do much testing for that. The group by operation we can just import from itertools, so we don't really have to write much code for that either. The part that really, I don't want to say threw me for a loop, but that took me a couple minutes to figure out here was the dates, calculating the time between the dates. And so for that, I knew there's the datetime module, which is used for handling dates. Time and date is one of the most complex data types you can think of. There are so many different standards around the world. It's really actually quite difficult. We could do a whole lecture series on just dates and times. But for now, let's just solve the problem at hand. So what I did is I Googled, and I found a guide on kind of custom datetime string formats, because this string format here that's not a standard string format anywhere. At least it's not the standard American string format as far as I could tell. So there was no like standardized way of reading this in. So we had to write a formatting string that basically deals with how this is formatted in these strings. And then we have to pray and hope that this formatting is consistent across all items in our data set, right? We're just looking at a single item here, and we hope that it's representative of all of our data. Very oftentimes this will not be the case, and your code will break once you then apply it to all of your data. But it's easier to test on just a subset of your data, which is what we're doing here. All right, so I'm not gonna click on that link, but the bottom line being we're gonna import datetime from datetime. And then we have this kind of formatting string here that we wrote. And you can see that there's a bunch of percent signs. And so the datetime module understands each of these like percent signs and whatever like letters after that to mean a certain thing. So this, for example, means this is the month, but in a zero padded format. So January wouldn't be 1, it would be 01. And then the same for the day. And then here the year, uppercase Y means the year, but including the century. And then this is, again, 0 padded hours, 0 padded minutes, 0 padded seconds. And then this means PM or AM. And so this way, basically, given this datetime formatting string, datetime can now understand these strings and convert them to datetime objects. And so I'm going to write, calculate the time difference for a dummy object, and that's going to be datetime dot strip time, which what this does is it converts a string into a datetime object. And so we're going to convert the end datetime into a string object using this, telling how the conversion should work using this formatting string. And we're going to do the same thing for our start date time. So what we're doing is basically we're saying the end date time minus the start date time is going to be our time difference, right? That makes sense. And then I'm just going to say, well, how many seconds are there in an hour? Because the only way to kind of convert this to a single value is to convert this into total seconds. And I lied to you actually earlier. We're not going to look at how long these are in days. We're going to look at how long these are in hours, because I found that that's like the resolution I wanted to look at, because some of these permits are really short, and so then having 0.001 days is not really a nice way of looking at your data. And this was kind of more to my liking. So what we're doing is we're dividing our time difference. We're dividing the total seconds over time difference by the amount of seconds in an hour. And here I'm just doing some fancy string formatting to only include the first 3 digits after a comma. And so this first shooting permit lasted 26 hours. Okay, so we figured out how to, for one example, take the end date time and the start date time, convert them both to datetime objects, and then calculate the time difference. Now let's turn that into a function that takes in a row from our data set and returns the time difference in days. And so I'm calling this function here time diff, and this time diff is going to take in a row, and the rows in our data set are events, so I'll call this event here. It takes in a datetime formatting string. I've supplied this datetime formatting string a default argument here, which is the one we're going to use here. But oftentimes it's nice to, when you know that this is something you might want to change later, to already just pop this into the argument section and give it a default value. The seconds divider is basically how many seconds there are in an hour. This is another one of those things, maybe later on we decide we want to have it in days, and the time in days instead, or the time in weeks instead. We don't really know until we've looked at all of our data. So it's useful to just pop that into the argument section of our function. And then we can still change that later on. And then I've written like a nice little doc string here. So when I look at this code again tomorrow, I will still know what it does. And then I make it really easy for myself here. I just call this start date time, and to that I assign, again, the start date time, and then I do the same thing for the end date time, right? Again, we're using datetime strip time to convert this time string using this formatting string we made, and then I calculate the time difference, and then I return the time difference, total seconds, divided by our seconds divider. And just to test this out for our dummy object, well, this gives us the same 26 hours that we got before. And from there, we can actually go and just put it all together. And maybe I should have really copied, because by this time in the process, often we forget what we've actually set out to do. So it would have actually probably been good to, it did not take the AM, sorry. Didn't the permit actually last 14 hours? No, it lasted 26 hours. It did not take the AM, PM into account, you're right. It should have taken the AM, PM into account, because we have this P strip here. Zip. Let me just quickly copy and paste this reminder text in here, and then I'll take another look at our items here. They were on different days. So oh, that's quite interesting. Yeah, this should have been 14. This is quite weird. Why I didn't get that. Huh. This is quite odd. It didn't take that into account. Another mystery. Well, this is going to have to be a mystery for another day. I don't think we'll have time to look over that today. Again, dates are pretty finicky to deal with. But let's assume for now that this actually works. And let's put together the code to filter the data, to group by, borrow, and then we parse the start and ending time and calculate the time difference in days, and then we calculate our aggregate statistics, right? So we're gonna use, we're gonna filter our data by our film data, and we're just gonna use the Lambda function for this, ask if the event type is shooting permit, and then we are going to take that filter data here, and we are going to sort the filter data first by borough, again, using a Lambda function. And then we are going to group the data by borough, again, using a Lambda function. The reason we have to sort this beforehand is this is just how the group by works in H should be, oh, there we go. Yes, thank you, Mark. Thank you, Mark. Mark coming in for the save. Yep, and this just reflects my inexperience with time formats. Okay, so it turns out percentage H in our string gives 24-hour time format, and that somehow overruled the AM PM. Good to know. All right, let's get back to the code to answer our actual question, which is we're done filtering our data. We use the Lambda function for that, and then we take the filter data, we sort it by our by borough, and then we group that sorted filtered data by borough using this group by function. And then we are going to do, we are going to make a dictionary out of this grouped this grouped film data. And to make this a nice dictionary, what we do is to our grouped film data, we map a Lambda function, which takes in this grouped object, which is what this group by returns for each group. And we're going to turn that into a tuple, and we're going to take the 0th item out of this grouped item. That's the group name, if you remember from earlier. So that will be Manhattan or Bronx or Queens or what have you. And then the second, the first item in this grouped object is the iterable, which includes all the items that were actually picked out using our group by function. And what we're going to do is to this grouped function, to this grouped iterable, we are going to map our time diff function, which calculates the time difference. And we are going to just use lists to consume that map object here. And let's take a quick look at permit time by borough. This is what that looks like. It's basically a bunch of lists, and I should have probably collapsed this. And zip, yeah, you can see this is quite a lot. Let's say permit time by borough Manhattan. And we can see this basically gives us a huge list of different hour values here. And then what we can do is we can use, actually, from one of the previous lectures, dictionary comprehension. And we're almost at time, but bear with me like for a couple more minutes. We're like basically done at this point. So we have basically this dictionary where the keys are the boroughs and the values are basically a list of time deltas. And then what we are going to do is we are going to, for each borough and time deltas in this permit by boroughs.items, we are going to make a new dictionary item where the key should be, again, the borough. And the value should be another dictionary, which has for mean, well, the mean of the time deltas, and for median, the median of the time deltas, and for standard deviation, the standard deviation of time deltas. And let's calculate this again. And what we can see is in this relatively little code, we've calculated these somewhat complex statistics over our data. So we know in the Bronx, the mean and median are relatively close. They're about 15 hours per permit. The standard deviation, however, is 6 hours. So clearly there are some permits that last quite long and some that are last quite short. And for Brooklyn, it's relatively similar. And we see that for Manhattan is the only one where the median is a bit larger, but the median corrects for that. And so it's again a note that maybe the median sometimes is a bit of a better way to look at things. And we see why this is the case here, because the standard deviation is 84 hours. So there must have been some enormous shooting permits in Manhattan. And Queens, again, relatively tame. And Staten Island has the least amount of standard deviation. So there it's most consistently between like 15 and 20 hours-ish. So just to wrap up real quick. Today we've learned about some higher order functions, especially map and filter. We learned how we can use these higher order functions in conjunction with iter tools and a bunch of other tools and maybe our own defined functions to answer really complex questions. Like I really don't want to overstate, but this last kind of question we answered is, I would say, relatively complex. And given the amount of code we had to write, we got away with relatively little code. We learned a little bit about generators. Again, there's a section with a little bit more on generators for the extra curious when you scroll down here. You don't have to read this. This is just if you want to know a little bit more in depth about what's going on in there. In our data analysis example, you may have noticed that we had to jump to some hoops to kind of analyze the tabular data in our CSV file, because it's not super easy to kind of keep track of all the columns in our data at once, and kind of do relations between the different columns. And just this whole, like, we have to write a bunch of extra code just because we don't really have dedicated infrastructure for that in base Python. And that's why next lecture you're going to learn about two packages that are kind of core to data analysis in Python and abstract away a lot of these hoops and a lot of these thinking patterns with lambdas that we did, that we have to jump through in regular Python, while also being about 100x faster. And those libraries are NumPy and Pandas. So definitely don't miss the next lecture and the following ones. Another thing you may have noticed is we still haven't really done any plotting, because plotting in base Python is kind of a pain in the neck. So we're also going to learn about matplotlib in one of the upcoming lectures. So stay tuned for that as well. Finally, I wanted to close with some of my favorite Python talks. Again, if you find that you really want to get into this, there are two useful talks that I recommend watching. One is by Raymond Hettinger and one is by Jake Vanderplas. And here's some just kind of interesting and slightly provocative talks if you're down to nerd out a little bit more on this topic. And again, here's a bit of another section on generators, explaining a bit more how they work internally. And that's it from me. Thank you for sticking it out for an extra 5 minutes. And if there are any more questions, let me know. Ping us on Stack Overflow as always. And thank you everyone for coming in. Thank you to the organizers, to the folks in the chat. Thank you to Mark for saving the day with that time formatting string. And yeah, if there are any questions, I'm more than happy to answer.